So it's been a while since we've done limits. Some of these are fairly simple, and some of them are a little bit harder. And some of them you might not remember. There we go. But there's the answers. The first one you can get just by plugging in. For any limit, how should you always start? Always plug in the number, right? Because sometimes you can just plug in the number and get out the answer. So for this one, you plug in the number. For this one, you just have to simplify the fractions, right? You've got to combine the fractions, clean it up. This is the one that everyone got stuck on in first period, so we'll walk through this one. This one, how do you do this one? Right, you got to rationalize. So you have to multiply top and bottom by the conjugate. This one, whenever you have a limit as x approaches infinity, we're talking about horizontal asymptote rules, right? When the degrees top and bottom are the same, it's the quotient of the leading coefficients. If the bottom is bigger, it's 0. If the top is bigger, it's either going to be infinity or negative infinity. And the easiest way to determine which one is just to plug whichever infinity, if it's positive or negative, plug the infinity in and check the signs. So for this, you get a positive over a positive, so it's positive. All right, the only one that's unusual is this guy. When you plug in the 5, you get 15 over 0. When you have not 0 over 0, what's going on the graph? A whole would be if you have 0 over 0, right? So what's the other option when you divide by 0? You have an asymptote, right? Good. So for this guy, we've got a vertical asymptote. When you have a vertical asymptote and it's not asking right or left, you got to check both sides, because depending on, we're going to go through this. Depending on your function, right, it could either say that's 5, so you could either do this, right, and then it's pointing up to infinity, or it could do, it's pointing down to negative infinity, or it could do this, right, one's up, one's down, or the other way. One's down, one's up, right? If it's this or this, then the limit wouldn't exist. If it's this, none of these, the limit technically exists, but this one we would write infinity, and this one we would write negative infinity. This we would write d and e and d and e. So how do we know, right? So the proper way to do this is to check both sides and check if it's going to positive or negative. Now, I'm not sure how Mr. Thomas taught you to check limits at vertical asymptotes left and right. Ah, that's exactly what I do. So yeah, great minds, right? Okay. All right. So here's what I do. Say you have to check the limit as x approaches 5 from the left. This only works with vertical asymptotes, right? If it's another limit with 5 from the left, you just plug in the 5, right? But for a vertical asymptote, if we want to know if it's going to positive or negative infinity from the left of 5, pick a number close, like 4.9, and just check and see if it's positive or negative. So you'd have a positive over a negative. So this one is approaching negative infinity. Here, if you pick something like 5.1, you get a positive over a positive. This one's going to positive infinity. Since they don't agree, the limit does not exist. Right? Does that make sense? It's been a while, right? Oh, those days, back in September. All right, so today we're going to learn l'hôpital. Okay? All right. And what does l'hôpital mean in French? It means the hospital, right? This is Mr. the Hospital's rule. All right, so we're going to use l'hôpital's rule to evaluate limits in indeterminate form. What do you think indeterminate means? Can't be determined, right? Undetermined, right? Okay, so indeterminate form really just means, who's that handsome guy, right? So anyway, indeterminate form means if you plug a number in and you get something where the limit's kind of undecided, either 0 over 0 or an infinity over infinity kind of a thing, right? So anytime you plug in a number and you don't just get out an answer. All right, so Guillaume Francois Antoine Marquis de l'Hôpital was a French mathematician with a really good wig. And he lived from 1661 to 1704. He was yet another buddy of Bernoulli. My students last semester, we kind of walked through some mathematicians, and Bernoulli got around. So he was friends with a lot of people. Anyway, so Bernoulli tutored him privately on infinitesimal calculus. L'Hôpital was sneaky. He was smart. He was kind of crafty. Here's what he did. In 1694, he made a deal with Bernoulli. He would pay Bernoulli 300 francs a year if Bernoulli would tell him all of his mathematical discoveries without publishing them. So Bernoulli agreed. And for years, not forever, but for quite a few years, Bernoulli went to L'Hôpital, told him all of his discoveries, and got paid his 300 francs. And then L'Hôpital took Bernoulli's work and published it under L'Hôpital's name. So, 1696, in 1696, L'Hôpital published his first book. This is all on differential calculus and differential geometry. If you want a serious challenge in college, say after you finish Calc 1, Calc 2, Calc 3, this is kind of Calc 2, right? You can take Calc 3 with Mr. Thomas next year. But anyway, after you finish all of your regular calculus, try differential geometry. Whew, it's a fun one, right? It's the only time I ever had to deal with functions with n dimensions, right? So, yeah, nth dimensional differential geometry. It was my, if I remember right, that was one of the hardest classes I ever took in college. So, okay, after L'Hôpital died, Bernoulli tried to convince the world that the book was actually his work. Nobody believed him, right? He's running around trying to tell everybody, no, I really came up with all of that, and he just took credit for it, right? And nobody believed him, and nobody believed him, and then Bernoulli died, right? And then 300 years later, really about 200 years later, somebody's in a library in Basel University, or Basel Universities. Is it Basel or Basel? Basel? Basel?
Because Basil, B-I-S-I-L.
Like Basil Rathbone? Really? The original Sherlock Holmes? Okay. Anyway, all right. So, Basel University, dating back to 1691, he found a manuscript of Bernoulli's tucked away in this library that dated 5 years prior to when L'Hôpital published his book, and it was pretty much the whole book in Bernoulli's handwriting, right? So, anyway, yeah, so he kind of, I don't know, gave credit to Bernoulli, but of course Bernoulli was dead, right? So, yes.
How did Bernoulli not see that coming?
I know. I'm sure he did. He just got frustrated. I don't know.
He was the first.
Yeah. He needed money, right? Why do people do things? Mostly, like, the biggest reason that people do things that they know aren't good for them is because they need the money. Well, most of them, not all of them, but often. Anyway, moving on. Okay, so here's L'Hôpital's rule. So this is named after L'Hôpital, even though L'Hôpital really didn't write it, he just published it, right? Okay. So, there's so many theorems like that that are named after people that didn't actually come up with them. So, look at Pythagorean theorem, right? Everybody thinks Pythagoras came up with that. So, oh gosh, that theorem dates back thousands of years. I think some people say that it was Chinese who came up with it originally. I think that's the oldest dating of the use of the Pythagorean theorem, but it's not like one person that's credited for it. So, but Pythagoras did write the first published original proof, so he's got that for him. Okay, so here's L'Hôpital. Here's what it says. If you have a limit of a function over a function, and you plug in, and you get 0 over 0, or any infinity over any infinity, positive or negative, doesn't matter, as long as it's an infinity over an infinity, right? Or 0 over 0. If you get either one of those, then that limit that you started with is equal to the limit if you took the derivative of the top and the derivative of the bottom. Now, big note, this is not quotient rule. It's the only time that you get to do a derivative of a quotient without using quotient rule. So, you have a top function, you have a bottom function, you literally do the derivative of the top and divide by the derivative of the bottom, and that's it. And then you have an equivalent limit that is hopefully simpler and something that can be solved. All right. So, here's what I want you to try. I want you to try some of those warm-ups and see if you can redo them with L'Hopital. Some of them, L'Hopital won't work, but some of them it will. So all you have to do, just remember to plug the number in first, because if you plug in the number and get an answer, you're done, right? But if you plug in the number and you get 0 over 0 or infinity over infinity, try L'Hopital and see what happens.
So leave using the low.
For 2
For 2 is -5. Well, only for 0 or 0.
No, first one you can't do it, but do you really need to do it on the first one? There's a couple where you can't do L'Hopital. Most of them you can. 6 meaning good? Yeah. 6 means good? Okay, okay, good.
It's a bit outdated at this point, but you no longer
That's rad.
Rad's from like the 80s.
Yeah, from the 80s. My dad says that. I think from the 80s.
I never heard of ice.
No.
Yeah.
Then you just plug
in 0?
It's like that.
Like spicy good?
No.
Okay, so anyway, let's get back to work. Keep focusing on the math. You're so amazed. Like, oh my gosh, it really does work. No way. No, you can't do it with the third one. You can't do it with the first or the third, right? Because when you plug into the first, you get 0 over 4, so that's just 0 and you're just done, right? When you plug into the third, you get 15 over 0, so L'Hopital does not apply. So you have to do the method that we did on the front screen, right? But you can do it on 2, 4, 5, and 6. I love it, especially for limits as x approaches infinity, if you are uncomfortable with horizontal asymptote rules. It's really nice.
that's just a negative one.
So this way, one side. Minus 5.
Yeah.
Wait, no, wait, so I,
The twos cancel.
And then it's probably zero.
No, so then you have to cancel the X.
Well, you don't need to. Oh, yeah, no.
How are you doing so far, 1 through 4? Good. Feel okay? All right. This, see, to me, it may be a little bit time consuming, but I think this is so much faster than rationalizing, right?
Yeah.
Okay. For number 5, if you do those limits as x approaches infinity, so here we get infinity over infinity, so we take the derivative, we get 6x over 2, which is basically 3x, right? What is 3 times infinity? It's infinity. All right, for this last one, so we plug in and we get infinity over negative infinity. Is it okay that it's a negative infinity? Yes, sign doesn't matter, right? So derivative of the top, derivative of the bottom, done. Right? So it's pretty slick for a lot of problems. There's a few, once in a while you get ones that it just doesn't work, right? But for the ones where it does, it's handy. All right, here's a fun one. Now, suppose we had this limit. I'm going to just give you a break and tell you that if you plug a 3 in, you get 0 over 0. So take a second and try L'Hopital this way. Yeah, I use L'Hopital as a verb all the time. Just show it to me now. So did you get the first step?
Do it again.
That's a big help.
So when you get to here and you plug in the 3, what do you get?
0.
You still get 0 over 0, right? So for this first one we plug in, we get 0 over 0. For this one we plug in, we get 0 over 0. Whenever you have a limit that when you plug in you get 0 over 0, can you L'Hopital? Yeah, L'Hopital again. Yep. So now you plug in and you get 18 minus 8 or 10
Wait a minute.
over 18 minus 2. It's not bad, huh? Especially since if you were faced with the original problem, they don't factor easily, right? Grouping doesn't really work with this. So you'd have to plug in 3 over 3. Now, here's the one saving thing for you if you didn't have L'Hopital, is if you plug in a 3 and you get 0 over 0, then you know x minus 3 has to be a factor from both, so you can synthetically divide it out of both, right? And then get an equivalent limit, but you'd have to do that, and then you'd still end up with quadratic over quadratic, and you'd still have a 0 over 0, so then you would still have to factor and divide. Yeah. Okay, so I want you guys to take a minute. There's 4 more to practice with. See if you can figure out which of these you can use L'Hopital with, and try it.
Probably, yeah.
Anyone else agree with Arcane?
One over square. It's X squared.
That's the question. Can you use that? What is that? That's like someone ordering a sandwich. Yeah. What? Fight me. Brought to the sandwich. Yeah, sandwich. What's the problem here? That's all.
Everything, we okay with that?
We're good. We're good.
And Stephen, are we okay?
That's sandwich.
You guys doing all right? Okay. Start on there.
That's a restricted study. That's a restricted study.
What's a restricted study? Yeah. Yeah. We're talking about the derivative. It would be easy. Oh, yeah.
Very good.
Wait, no.
Absolutely. Be like super. Yep. Our next lesson, I had this awesome discussion. Not really, but I had so much fun researching. I didn't even hear as much of the stuff that I found. But negative, I'm so excited. I just got all jazzed up. I was like talking about all the natural going. That is so cool. So excited.
This gets bigger, this is gonna go to 0.
Was that you? You have a question?
Yeah, you got it. Always right. You don't even know.
I knew.
So we got a 50 over
What's infinity squared?
I feel like this would be a perfect fraction.
Yes. What is 2 over infinity?
Wait, what?
2 divided by infinity.
Is zero.
Or like,
Yeah, wait.
Zero?
Why is there zero?
It's like,
that's
2 is 0.
There's the first 2 for you.
Is 0, I do what I got.
Any questions on either of the first 2? Remember when you have a constant over infinity, that's essentially 0, right? Yes.
So if you get infinity over infinity, is that now okay?
No, that means you have to L'Hopital again.
But we'll just do one.
It depends on the degree of infinity,
The infinity is just.
right? Okay.
number 3. I'm not really sure.
That was actually a governor's honors interview question.
What do you get for free?
Do you guys have a 2 extra program here?
And then
We're, we used to have this thing you had to apply for it.
Why
You
X?
go, you picked a subject, it was only for a few kids each summer, but you, say you really loved math, right? So you would apply for governor's honors for math, and then you have to go through a series of interviews, right? And after all these interviews, the candidates just get narrowed down and narrowed down, and then if you are one of the candidates, then you get to go for 6 weeks. 6 weeks of your summer, and it's an all expenses paid, like, math symposium, right? Yeah, where you like really become in-depth in math, right? Yeah, it is actually very cool. So we had one of our students, one of my students went, a number of years ago, and he was already like smart, right? He already loved math, and he was a sophomore. He was a BC Calc student, and he went to governor's honors, and he was like amazo math after that, right? He was so amazingly brilliant, and so he was on our math team, right? And so after that, we just started winning like crazy, right? Once he went to governor's honors, and now he's a math professor at State University of Pennsylvania. So, yeah, and that was from governor's honors. Governor's honors were great for. But anyway, I used to do the interviews, right? So once every couple of years, I would volunteer, and one of our questions was, what is infinity divided by infinity? And then the candidate would just have to sit there and discuss, right? No real right or wrong answer, you just have to hear their view.
Well, that's an awful interface.
One is a view, can you justify it, back it up?
Hold up, so then
Divides and divides all.
back to the
Okay.
top, so it would be zero.
So what I give you is program.
Len, 0 divided by 0 is 0.
I love it.
It doesn't
Yep.
exist, so anything divided by itself doesn't apply.
Okay. So
Out of the
anyway,
program.
so this one, did you guys get infinity?
You're ugly.
Any real numbers except
Okay, so for number 4, you do the derivative, right?
except 0. Oh no.
There we go. Okay, oh no, I gave it away. So, you do the derivative, and you end up with another infinity over infinity. You do the derivative again, and what do you end up with? The original problem. You end up with the original problem, right? So you end up with this whole circular argument thing that just leads you back to where you started, and then you're stuck. This is one of those cases where L'Hopital just doesn't help you. So, when L'Hopital doesn't help you, you have to do the limit using old-fashioned means. Now, we have talked about limits at infinity. What is that? Oh, I actually put the answer up. Oh wow, look at that, my hand wrote it, it's right here, I didn't know it was right there. So anyway, okay, so we have done limits as x approaches infinity in the past, and just so all students are on the same page, when x is approaching infinity, any terms beyond the leading terms become insignificant. So what happens is, it wouldn't matter if this bottom was the square root of x squared plus 10 million x plus 800 trillion, right? Those 10 million x and 800 trillion eventually will become dwarfed by the big giant infinity leading terms. So you have the right, and it is absolutely correct, to drop all terms after the leading term when you are doing limits as x approaches infinity. The big thing to remember here, let's see if you guys remember this, is that when x is positive, the square root of x squared is x. When x is negative, the square root of x squared is negative x. Negative x. So that's the trick to remember. Alright, so when x is positive, square root of x squared is x, you get x over x, so the limit is 1. So that's the old-fashioned way of doing it. Alright, just for fun, so that's enough L'Hopital for the day. We're going to do more L'Hopital on Tuesday. But just for fun, we have 3 awesome integrals here. These integrals review concepts that we have learned not only in this unit, but a couple little concepts from last semester. So these are really great integrals. The first one is, I don't think any of them are really that terribly difficult, but to me the first one had the most steps. There are two approaches for the first one, that, at least two that I am aware of. There could be more, but there's two. If you were going to start the first one, what would you do? You would honestly FOIL that whole thing out.
Use the Pascal.
You know what? It's not a terrible thing. I mean, it's only to the fifth, right? You can do binomial expansion and have that sucker FOILed out in probably 2 or 3 minutes and probably be faster than the way that I did it, right? So, yeah. The only problem though is that the answer, if it was a multiple choice problem, which it would be on the AP exam, would not be, you'd have to sit there and figure out which one's equivalent to what you have. Because it wouldn't be written as a big giant polynomial.
I didn't make you mess
Anyone that's in here could have made them out. I had one student who went from AB into. Wait, what are you doing? Yeah.
Wait, how are you doing
You what? You did? Alright. So for the first one, I will tell you, does anyone have any other ideas apart from FOILing the entire thing out? Yeah. Good? Integration by parts. You can try that because it is a product, right? And when you see products, it makes you think integration by parts. It doesn't work well. So when you try it, after like 1 or 2 iterations, you're going to just start saying, you know what, this is not working out well. So I'm just going to spare you the pain right now from integration by parts because it just won't help you. Did you have another one? No, because that's just integration by parts. Integration by parts tab method only works if you have a polynomial times something that you could easily, repeatedly integrate. And since you don't know the integral of 1 minus x squared to the 5th, you would have trouble with that one. Yeah?
Can you do a special case use of?
You could do a special case use of, and that is one of the 2 methods that we used this morning. I did not do a special case use of, but you could, right? So you could let u equal 1 minus x squared, get your du, and then you would have to solve for u and cube it and, you know, get, or your x and cube it and get that.
Wouldn't an x be thrown outside though?
An x would be thrown outside, yes.
Yeah, okay.
So you'd have an x squared, you'd have to solve it, which wouldn't be that terrible, kind of mediocre, right? So you could do a special case use of. There's one other method that we have learned.
Could you make it the square root of 1 minus x squared to the 10? I do it triangle.
Okay, so what I did, wow, I don't even have it up here. I'm just gonna write it then. Okay, so what I did was I rewrote this as the integral of x cubed times the square root of 1 minus x squared to the 10th. Because 5 is really the same thing as 10 halves, right? Once you have a square root of a quadratic, you can do a trig sub. Try it. Go from there. Take the answer away so you can. Yes.
Oh, it's gonna be one of those.
Right, if I remember the answer correctly, I think that is right. Yeah.
Oh, isn't that how?
Like everything. I'm sorry.
I just apologize.
At the beginning of everything.
How would you, okay, but now you have to do your integral of that. Oh, which is use, oh. You are. But it's not terribly far off. Yeah. So. This should be in negative 1.5. Am I thinking correctly? Or here, I'm sorry, you guys line yours differently. Oh, okay, so you have negative 1.5, and then you the 6, oh yeah, you got it, yeah. Do you need it? And then x squared to 6, perfect. Yeah. Okay, so oh wait. Okay, there's just a little tiny coefficient thing, but yes, what you're doing is correct, it could work, yes.
Before you self.
Just check your coefficient.
There's no way.
The integral of sine.
Yeah, that's right. You got it.
For what? What?
Plus?
Like that logic.
Yeah.
Did that?
See, I did, I have a negative in front.
Yeah.
I just haven't solved that with video.
Cosine 11 theta?
Yeah, I'm definitely seeing some great methods. I will tell you guys, someone just figured out how to do this with an integration by parts. Yeah. So what they did was they split it into an x squared and then an x times 1 minus x squared to the 5th. So that you had an x available for your u sub on your integral.
I'm gonna try it that way.
Yeah. I think that's right. Here, I'll show you the answer. So I did it in quite, now I'm like, the more I look at mine, I'm thinking, wow, there are actually some simpler ways to do it. So, something equivalent to that, is that what you got? Oh, wait.
Oh my.
There. Alright, so I did with trig substitution, but when you do a trig substitution, you get a product of sine and cosine with odd exponents. So this is going back to where you have to pull out a sine, and then take the sine squared, write it as 1 minus cosine squared, distribute, and then you get your little u sub with your cosines and convert. So my way didn't feel bad when I was doing it, but I'm seeing other people doing a special case u sub where it worked fairly nicely, and I'm seeing people do an integration by parts where it worked fairly nicely. So there's more than one way to solve an integral, right? Number 1 was the most difficult. 2 and 3, take a look at the denominators and what do they make you think of? They both factor, so 2 and 3 are probably what? Partial fractions. However, there's a gotcha. People are forgetting a very important rule about partial fraction decomposition. What is that rule? Why can't I do an immediate partial fraction decomposition on number 2?
The top is greater than the bottom.
Because the top has a greater degree than the bottom. For partial fraction decomposition, it not only can't be greater, it can't be equal to. So you have to divide for both of these before you start. So you're going to have to do division on both of them before you start. And the sneaky thing about partial fractions is if you don't divide first, you will get an answer, but it will be wrong. Yeah. Everyone who did a use of did do it faster. I kinda like that way better. I'm gonna ask Mr. Thomas, when he and I were speaking about it before, because you can also do special case use of on some problems that would be long division problems. And, like, you could technically do number 2 with a special case use of, what the advice I was given was that when in doubt, the division is better, it's your better bet to go. So my thinking was, same thing for the special case use of number 1, that when in doubt, do the trig sub. But number 1 really does work faster with the special case use sub. It really does. It cuts out the whole middleman.
Yeah.
Yep.
Can you do like an integration by parts for it?
Yeah, you can. Oh, you want me to show you? So if you set up your integration by parts, your u would be the x squared, and your dv is this big thing right here. So just go ahead and write it out. Your u, so then you need, and your dv is x times 1 minus x squared to the 5th. And now you'll have to find du, and you'll have to find v.
I don't
You have to divide first.
Divide it out. It's not that bad.
Yeah, it's really not.
I like the long division ones because it's going to be simple when you're done long division.
I agree. I agree.
When you get the remainder you on top, you divide it by. You're dividing by x squared minus 4 the whole time, right?
Yeah.
You're taking that out. So at the end, you keep dividing by x squared minus 4 goes on the bottom. You do long division and you get like 16 on the bottom, right? And so the whole time you're dividing by x squared minus 4.
Okay, check your division, make sure that you got the correct answer to your long division for each one.
You wouldn't all of a sudden multiply by x squared minus 4. Keep dividing by it.
Yeah. I'm just showing you the first step. That's a separate problem.
God, Lindsay.
Oh, no, sorry. Okay. Yeah.
For both of them, or just the number 3? Yeah, you have to divide it, but you can't divide it. Need some help. For, to go from like that's your point. It's what, but that can't be right. Let's see. Oh, wait. You pulled the 48 out front, that's why. It's recording. Oh.
So you did all you.
Because 40 divided by
No, it likes that. Oh, 4A is 1, A is nothing.